All right. Now, we erase the machinery and start over. This time, we start with electrons. We have a filament here, tungsten plate, holes in a tungsten plate, and for a detector, any electrical system which is sufficiently sensitive to pick up the charge of an electron arriving with whatever energy the source has. Or if you would prefer, we could use photons, and this is a black paper with a hole in it, 2 holes in another sheet of black paper. Paper isn't very good because the fibers don't make a sharp hole, so use something better. And here, for a detector, a photomultiplier that can detect the individual photons arriving. Now, what happens with either case, and I'll discuss only the electron case, the other case is exactly the same, the case with photon, is this. First, that what we receive in this electrical detector with a sufficiently powerful amplifier behind it are clicks. Click, 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 and so on, with the source here. Lumps. Absolutely lumps. When the click comes, it's a certain size, and the size is the same. If you turn the source weaker, the clicks come further apart, but it's the same size click. If you turn it up, they go click, 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 and it jams the amplifier. So you have to turn it down enough that there aren't too many clicks for the machinery that you're using to detect. Next, if you will to put up another detector here and listen to both of them, you never get 2 clicks at the same time, at least if the source is weak enough so that, because of the precision with which you measure the same time. If you cut down the intensity of the source so they come few and far between, they never come a click in both detectors. So that means that the thing which is coming comes in lumps. It has a definite size, and it only comes to one place at a time. All right, so for electrons, or for photons, we'll just use it. It comes in lumps. And therefore, what we can do is the same thing as we did with the bullets. We measure how many come, we measure the probability of arrival. What we do is we hold the detector in a certain place. Actually, if we wanted to, although it's expensive, we could put detectors all over at the same time and make the whole curve simultaneously. But let's suppose we put it in a certain place and we measure at the end of an hour how many electrons came, and we average it. By the way, if I put detectors all along the back here, when one comes, it comes into one, but not from others. It just one goes off, then the other goes off, then this goes off, then that one goes off, so on. Just like with bullets. And we measure then the probability of arrival of the electrons. And what do we get? The number of electrons that arrive. The same kind of an N12 as before. This is what we get for N12. N12 is this what we get with both holes open. And that's the phenomenon of nature, that she produces the curve, which is the same as you would get from an interference of waves. But she produces a curve for what? Not for the energy in a wave, but for the probability of arrival of one of these lumps. The mathematics is simple. You change I to N, and you have to change H to something else, which is new. You call it something because it's not the height of anything, but in order, this curve has a simple mathematical form. There's an A, which can be represented as an A1 plus an A2, which we call a probability amplitude, because we don't know what it means, which to arrive from hole 1 plus the probability amplitude to arrive from hole 2, and you add the two together to get the total probability amplitude to arrive and square it. Just direct imitation of what happens with the waves, because we've got to get the same curve out, so we use the same mathematics. Let's find out, I better check on one point, though, about the interference. I forgot to say, what happens if we close one of the holes? Let's try to analyze this interesting curve, which now, for electrons, I erase all the stuff with the light. Well, everything with light is erased. And now we're talking about electrons. This curve isn't important in our case. This is the number which arrives. Now, we would like to analyze this curve. And we try this. We say maybe it comes, we can analyze this by thinking that the electrons come through this hole or through the other. So we can close one hole and measure how many come through hole number 1, and we get that curve. Or we can close this hole and measure how many come through hole number 2, and we get that curve. And these two added together is not this, And so this is not the same as N1 plus N2. And it does show interference. It shows interference. And in fact, the mathematics is given by this funny formula that the probability of arrival is the square of an amplitude, which itself is the sum of two pieces. Now, the question is, how can that come about? That when they go through hole 1, they would be distributed this way. When they go through hole 2, they would be distributed that way. How could it be that when both holes are open, you don't get the sum of the two? Instance. If I hold the detector at this point here, I get practically nothing. If I close one of the holes, I get plenty. If I close the other hole, I get something. If I leave both holes open, I get nothing. If I let them go through both holes, I don't come anymore. Or take the point in the center. You can show that that's higher than the sum than it was in the other case, than the sum of these two. I get more here when both holes are open than I would get with either one of the two closed. Now, you might think that if you were clever enough, you could argue that they have some way of going around through the holes back and forth, and they do something complicated, or it splits in half and goes through the two holes, and so forth, in order to explain this phenomenon. Nobody, however, has succeeded to get an explanation of this that's satisfactory, because the mathematics in the end is so very simple. The curve is so very simple.